Hey, what's up? It's your old pal, Mr. Cook. We're going through this worksheet 2.5 AP Calculus AB extra worksheet. So, you've learned implicit differentiation. Implicit differentiation is when you have functions of x and y that can't be separated. Because if you can just get y by itself, then you can take the derivative with respect to y, with respect to x or whatever your variable is, and it's like pretty straightforward, pretty easy. With implicit differentiation, you can't separate the y all by itself easily. So you have to use other means. And this is what your teachers will tell you to do. What you basically do is you treat the x's and y's as like separate functions. So you take their derivatives like individually. Okay, so like you're basically treating x as a function and y as a function. But since we're taking the derivative with respect to x, when you take the derivative of y, you get a y prime or a dy dx at the very end. So like this is how it would look. If you take the derivative of an x, it's just normal. 2x, right? But if I did the same thing with the y part, I take the derivative of y squared, I get 2y, and then I'd write dy dx next to it, or y prime, whatever your teacher tells you to do. And then from there, what you do is you just like solve for the dy dx. You got to manipulate the expression algebraically, but the idea is just to get dy dx by itself. So we start off with number one. We're just going to do those steps over and over again. And really, the steps that I'm going to use for number one, listen to my words closely. I'm going to do the same stuff for two. It's like I have like an order by which I do these problems, and it helps me to keep things organized, and it's like pretty easy. So if I got x times the natural log of y equals 2, when I take the derivative of this, I need to recognize that this is like x, like a function, times the natural log of y, another function. So if I have a function times another function, what rule do you use in derivatives? Product rule. So you're going to use the product rule for this, okay? So when I use the product rule, I take the derivative of one part, so derivative of x is just 1, and multiply it times the other thing, so natural log of y. Then plus, I take the derivative of the other function. Natural log of y's derivative is 1 over y. But when you take the derivative of y, since there are two variables here, you need to write dy dx next to it, okay? And then times the other part, and I don't take the derivative of that, so this is x. Now, when I take the derivative of 2, it's just a constant, and the derivative of a constant is always going to be 0. So that doesn't change. So that's like the big change. When you take the derivative of the y part, you just write dy dx next to it, or multiply by dy dx. Okay, so next stop, we're going to get the dy dx all by itself. So next what you would want to do is move all the non-dy dx terms. So like, like this one, for example, this doesn't have a dy dx on it. This one does. I would move this thing to the other side of the equal sign. Okay, just like subtract it away. So let's do that. So this stuff is going to stay on the same side. So it's going to be 1 over y dy dx times x equals. And then I move the other stuff to the other side. So we get a minus 1 natural log of y. So now I'm going to make things look a little bit nicer. So like this x, I can just move it over here by multiplying it, right? So it'd be like x times 1 over x, and then x times 1 is just x. So we just move the x up there. And then I can get rid of that negative natural log and just write a negative on there. That's fine. So if I need to get dy dx all by itself, because that's what I'm solving for, dy dx, what I would do is I'd divide by x over y. In other words, multiply by the reciprocal. So I'm going to multiply by y over x. So times y over x. And that's going to be my derivative, okay, because it cancels out and it gives me dy dx by itself. So I just look for the one that looks like this or pretty close to it. Looks like B is going to be the one that I want. So that's number one. So here are the steps that I went through. Okay, so first things first, when I recognize that it's implicit differentiation, that's kind of just obvious. But first thing, I treat the x's and the y's as functions, and I do the derivative. I do the derivatives for both. Okay. The next step, all the stuff that has dy dx is on one side. And then the non-dy dx stuff is on the other side of the equal sign. Then what I do is so the third step is that if I have more than one dy dx, I will factor that out. So factor out the dy dx. And then the last part is I divide to get dy dx by itself. And this is my like general pattern that I use for all of these, implicit differentiation problems. Like that's what I just did for number 1. So if you go back with these rules written down and watch me go through the problem, this is exactly what I do. I'll show you that that's what I'm going to do for number 2 as well. So for number 2, I take the x's and the y's, I treat them as functions and take the derivatives. So if I just have like an x to the 4th all by itself, it's just going to be 4x to the 3rd. That doesn't change at all. But then if you look at the next part, negative x squared times y, well, that's a function times a function. So maybe like my first function would be negative x squared and my other function would be y. If it's 2 functions multiplying, you've got to use the product rule. So the derivative of negative x squared is just going to be a negative 2x. And then the y stays, itself, just like in regular product rule. And then I got to take the derivative of the other one, y. The derivative of y is going to be dy dx. So I just write, 1 dy dx right there. And then the derivative of, the y part is dy dx, and then the other part is just going to be the negative x squared, like that. Okay, and then I've got one last little part, the y to the 4th. So I take the derivative of y to the 4th, I get 4y to the 3rd, and then dy dx. And then the 1, when I take the derivative of 1, it doesn't matter if it's with respect to x or y. It doesn't matter. It's a 0. Any derivative of a constant gives you 0. So next, all right, so that's the first step. Got all my x's and y's, the derivatives, because I treat them like functions. Next, I've got to get the dy dx stuff on one side. Well, let me underline the stuff that is the dy dx stuff. It looks like that's this stuff here and this stuff here, right? These are 2 separate terms that have dy dx on it. And I know that they're terms because terms are separated by addition and subtraction. So like this is one term, this is another term, and then the other 2 are terms. This is a term and this is a term, but they don't have dy dx on it. So I move dy dx on one side of the equation, and then the non-dy dx stuff on the other. So you know what I'm going to do? I'm going to move all of the non-dy dx stuff, that's this stuff here. I'm going to move it over to the other side of the equation. Okay. So on one side, I keep all the dy dx stuff. So I've got dy dx times negative x squared plus 4y to the 3rd dy dx. It's all, normal, standard. And then on the other side of the equal sign, I'm going to have to move the other stuff. So like I've got a positive 4x to the 3rd. So if I move it to the other side, it becomes a negative 4x to the 3rd. If I've got a negative 2xy, if I move it to the other side, it becomes a positive 2xy. And then, so that's like completing the next step, moving dy dx on one side, the non-dy dx stuff on the other. The next thing is this. I've got to factor out the dy dx. Notice I've got a dy dx on this term, and I've got a dy dx on this term. So if you have common stuff on different terms on one side, you can factor that value out. Just like if I had like a 3x squared and like a 3 times 4y to the 3rd, I can like factor out that 3. Well, same thing with the dy dx. So I'll factor out the dy dx. And what do I have left over? I've got a negative x to the 3rd, or second power, sorry. And then I've got a 4y to the 3rd. Okay? And all that is equal to this other stuff, negative 4x to the 3rd plus 2xy. Now to get dy dx all by itself, I'm going to divide that last part out because dy dx is quite literally multiplying on all this stuff. So the way to get rid of it is to divide it. So that's why I do my last step. So factor out the dy dx, and then the last part is the last thing, get dy dx all by itself. So divide to get dy dx. So if I do that, I get dy dx is equal to negative 4x to the 3rd plus 2xy over that stuff, negative x squared plus 4y to the 3rd. So that's the derivative. Let's see what it's asking for. So I just know that like all these problems are going to require me to use the derivative at some point, but there are clues to it. Just in case you saw the problem, and you didn't know if you were supposed to take the derivative. It says here, what is the slope of the tangent line? That means find the derivative to this graph. And then if you want to find the slope of the tangent line, you find dy dx, and then you need a coordinate to plug in. And that's why you've got your 1 and 1 here. This gives you an x and a y value to plug in to get your dy dx, okay, to get your like actual value. So if I go down here to my derivative, and I do plug in 1 and 1. So the notation will look like this. Dy dx evaluated at 1, 1 would be equal to this. So if I plug in 1 for x and 1 for y, I get negative 4 times 1 to the 3rd plus 2 times 1 times 1 over negative 1 to the 2nd power. Oops, negative 1 to the 2nd power like that plus 4 times 1 to the third. So 1 to the third is 1, and 1 times negative 4 is just negative 4. 2 times 1 is just 2, so plus 2. Negative 1 to the second is just negative 1. And then 4 times 1 to the third is just 4, so plus 4. And then negative 4 plus 2 is negative 2. Negative 1 plus 4 is 3. So negative 2/3 should be my answer, B. Okay, moving on, number 3. So number 3, I got a function, find this. Well, what this means is find the second derivative. So what you do is you take the derivative one time, and then take the derivative again. Implicit differentiation usually follows from that, if you're already using implicit differentiation. So if I start off with x squared plus y squared equals 100, I'm going to do all my steps. So take the derivative, treating each of them like functions. So if I took the derivative of x squared, that would just be 2x. If I took the derivative of y squared, that would be a 2y. But every time I take the derivative of y, I put a little dy dx on it. The derivative of a constant like 100 is just 0, so I just put 0 there. And then I go through the next step. So put all the dy dx stuff on one side. That's this. It's already on this side. So I can just move the other stuff to the other side. So it looks like this so far. 2y dy dx is equal to, and then if I subtract over the 2x, I get minus 2x. Now I got to get dy dx by itself, but it's like being multiplied by this stuff, 2y. So I'm just going to divide both sides by 2y. And that'll cancel this part out, leaving just dy dx all by itself. And then the 2's cancel out, leaving me with just negative x over y. All right, so now when we have this, we have the first derivative. Now we got to get the second derivative. So for the second derivative, you just do the derivative again. So we write it out, d squared y over dx squared. The derivative for that is going to be what? Well, I've got a function over a function, so this thing is going to be the quotient rule. So I do the quotient rule, low d high minus high d low over low squared. So the low function is first times the derivative of the top function. So the derivative of negative x is just negative 1 minus high d low. So it's going to be a negative x times the derivative of the bottom. The derivative of y is just dy dx, 1 dy dx technically, all over the bottom part squared, so over y squared. Okay, so then if we just rewrite this a little bit, let's see. So y times negative 1 is going to be a negative y. And then a negative times a negative is a positive, so plus x times dy dx all over y squared. Well, oh man, how do we do this now? What the heck is dy dx going to be? Oh yeah, didn't we just solve for dy dx? dy dx is negative x over y, so that's what I replace it with. This dy dx, we already solved. It's negative x over y, so we just replace it in there. That's it. So that's our second derivative, but then we need to find the second derivative at this point, 6, 8. So we just plug in 6 and 8, and that'll give us our answer. So the second derivative, oops, that should be a y, sorry. Evaluated at 6, 8 is going to be this. It's going to be, let's see, negative y, so negative 8 plus x, which is 6, times negative 6 over 8, all over 6 squared, or sorry, 8 squared, so 64. All right, then let's see what else we've got. So negative 8, then minus 36 over 8 over 64. Maybe I'll just turn this into 64 over 8 and then subtract, so that'd be a negative 100 over 60 or over 8, sorry. Then if I multiply the 8 into the bottom, what would that give you? So 8 times 8 times 8 is, I don't know, well, whatever, 8 times 64. Now let's start reducing this a little bit more. I know that 100 and also 8 are divisible by 4, so that turns into a 25 in the top, and that would just turn into a 2. And then 2 times 64, I can do that in my head, 128. So is there one that's negative 28, 25 over 128? Yeah, there you go, A. So A would be the answer for this one. All right, so again, I'm just doing the same steps over and over again. Find the derivative, blah, blah, blah. Okay. 4. Get all this stuff out of the way too. Looks like we got to find the second derivative again, but we were given the first derivative. That's nice. So I'm just going to rewrite that. I tell my students in calculus, every time that you see a radical, rewrite it as an exponent. So if you have dx, dy over dx is equal to square root of 1 minus y squared, I rewrite that square root as that thing to the 1/2 power. Then it's pretty obvious what you got to do. This is a chain rule problem. So let's do the chain rule. When we take the derivative of the inside, this is just a function of y. So we're going to end up with a dy dx at the very end. So we get the second derivative, d squared y over dx squared is equal to, so the 1/2 drops out in front, 1 minus y squared to the negative 1/2 power times the derivative of the inside, which is going to be 1. The 1 goes away. So it's going to be a negative 2y. And then since we've been taking the derivative with respect to y, we write a dy dx at the end. And remember that dy dx is this stuff. Okay, so that's going to be part of it too. So square root of 1 minus y squared. It looks like we got to simplify this a little bit because none of these are the same thing. So let's do that. So it looks like everything's going to be a fraction. So we got starting off 1/2, and then this part has a negative exponent, so it's going to go in the denominator. So we get 1 minus y squared to the 1/2 power. And then we have like a negative 2y. That's going to stay in the top, so times negative 2y. And then we've also got this square root of 1 minus y squared on the top, because that doesn't have a negative exponent on it. So I see that like the 2's can simplify. So that turns into just a negative 1 overall because the negative stays on there. And then also, if I just rewrite this part, because it's a 1/2 power, that becomes 1/2 becomes the square root. So square root of 1 minus y squared. And then these will cancel out too, leaving you just with negative y. So negative y should be the answer B for this one. Okay. And then 5. So number 5, we've got to do, so consider the graph of that function, okay? Find the derivative, okay? And then find the vertical tangent line and the horizontal tangent line. Those ones aren't that bad, believe it or not. So, or the points where you have vertical tangents for those. So first we find the derivative. So we use the steps that we've outlined for implicit differentiation. So we take the derivative of all this stuff. Derivative of x squared is going to be 2x. Derivative of 4y squared is going to be 8y dy dx. Derivative of 6x is going to be 6. Derivative of negative 8y is going to be negative 8. Derivative of 9 is 0. And then derivative of 0, 0. So it just stays as 0. Oh, and I'm sorry. Since I took the derivative with respect to y on that last part, the 8, I got to do a dy dx. Sorry about that. I bet you probably saw that, right? Okay, next step. After I take the derivatives, get all the dy dx's on one side and then the other stuff on the other side. So this is my dy dx stuff. I got to move all the other stuff over. So I'll keep all this stuff here, dy dx. Then I've got a negative 8 dy dx. And then on the other side, I'm going to move the 2x. So I have a negative 2x and the 6, so minus 6. Now, same steps, factor out the dy dx's here. So I get, let me write the steps up here, dy dx times parentheses 8y minus 8. And then that's going to be equal to negative 2x minus 6. And then to get dy dx by itself, I divide that part out. So I get dy dx is equal to negative 2x minus 6 over 8y minus 8. So there's my first derivative here. Next, after I find the derivative, I've got to find the points where we get a vertical tangent. So what a vertical tangent means is that the dy dx stuff has the bottom part, dx, the denominator, is going to be equal to 0. So that's what it means. It just means like what x values get, what coordinates give you a vertical tangent. So the way that we are going to find that is by taking this function here and setting the bottom part equal to 0. So we're just going to take like negative 2x minus 6 over 8y minus 8. And a vertical tangent, again, has an undefined slope. So you just look for the values where it'd be undefined. So that's going to be pretty easy, actually, because the only way that this is going to be undefined is if the denominator, 8y minus 8, is equal to 0, right? So if you solve for it, 8y is equal to 8, and therefore y is going to be equal to just 1. So it's any point where y is equal to 1 on this. And let me think about this. So this is going to be an ellipse. So there's going to be a limitation on the x values. But I guess you could probably get away with just saying whenever y is equal to 1, that's when you're going to get the vertical tangents. Let me think about that. Could you do that in a different way? Yeah, I think that you could, because of the original problem here. It's equal to 0. Yeah, you actually can. You can. So when y is equal to 1, I was just thinking it's like any point, but you can actually find the coordinates on here. Well, that's pretty neat. Okay, so if we start off with our original expression, x squared plus 4y squared plus 6x minus 8y plus 9 equals 0, what we'd want to do is just set y equal to 1. So that becomes a 1, so 1 squared. And that becomes a 1 as well, so 8 times 1. So here's how it looks now. X squared plus 4 plus 6x minus 8 plus 9 equals 0. And then combine like terms. So x squared plus 6x. And then we've got 4 minus 8, which is negative 4. Negative 4 plus 9 is a positive 5. And this factors. So you've got x plus 5, x plus 1. Those are two numbers that multiply together to be 5 and add together to be 6. So that means that your two potential x values would be negative 5 and negative 1. So that gives you two coordinates where you have vertical tangents. One when x is equal to negative 5 and y is equal to 1, so negative 5, 1. And then the other coordinate's going to happen when the other x value is negative 1 and the y value is 1. So those are the 2 points where you have vertical tangents. Next, you want to find the points at which you have horizontal tangents. So horizontal tangents happen when the dy part is equal to 0. So that same equation, 2x minus 6, the derivative, and then 8y minus 8. You want the top part to be equal to 0. So set that equal to 0, and then solve for the x value. So if I add 2x to both sides, I get negative 6 is equal to 2x. Divide by 2, negative 3 is equal to x. So now, we do the same thing where we take the original equation, just like what we had over here, and then we plug in negative 3 for x and solve for the corresponding y values. So let's see here. The equation was x squared plus 4y squared plus 6x minus 8y plus 9 equals 0. So let's let x equal negative 3 and see what happens. So we plug in negative 3 for x. We don't know y. We need to solve for y. 6 times negative 3 minus 8y plus 9 equals 0. Negative 3 squared is 9. Then 6 times negative 3 is negative 18. So we combine like terms. 9 plus 9 is 18. Minus 18 is 0. So we just end up with 4y squared minus 8y equals 0. And this is an easy one to solve. If we factor out 4y from both terms, we end up with y minus 1. So that means that we end up with two y values. We get from this one, y could be equal to 0. And then from this one, we get y could be equal to 1 to solve this. So that means that we get two coordinates. When the x value is negative 3, the y value could be 0. So negative 3 is 0. And then when the x value is negative 3, the y value could also be a positive 1. So negative 3, 1 would be the other point where that happens. Okay, so there you go. That looks like the first page through number 5. I hope this was helpful. If you need some additional help, you can always go talk to your teacher, or you can always come by and see me before school or after school. I'm available most days. All right, thanks very much. Next video, we'll go through 6 and 7, and that'll be it. All right, thanks. See you then. Bye-bye.